Okay, so the other day, we very briefly talked about what an element was, and then we had to end the class because we were running low on time. This is kind of like chemistry 101, or I guess in the case for the college, chemistry 1120. You know, what is an element? And today we'll talk about what is an atom. Now, atoms and elements are basically the same thing, but there's a distinct difference. So an element is a substance. It's pure substance. So it's not a mixture of two or more elements or two or more chemicals or whatever. It's a pure substance, meaning it's only one thing. And we cannot break this substance down by chemical means. There's, physics talk about splitting atoms, but in chemistry, in chemical reactions, we cannot break these elements down any further. These elements are made up of building blocks that we call atoms. And I'll end today with, what is an atom? So there are, I don't know why that's not showing up. Hold on. There we go. There are 118 elements discovered so far. So there could be more. They tend to get a little unstable once they're in the higher numbers. But we've discovered 118 different elements, chemical elements to date. 94 of these elements are naturally occurring on Earth. So we can find them in the atmosphere, in the ground, in rocks, in soil, in creatures, in animals. Most of these elements are naturally occurring. The other 24 that we have discovered are synthetic. And the word synthetic means produced in the lab. We use nuclear reactions, so really complicated chemical reactions or nuclear reactions, I should say, to create these synthetic or human-made elements. So they do exist. They could be in the universe, but for us on Earth, we have to make them in the lab. And these 24 synthetic elements, they don't last very long. Most of them have a very short half-life, which we'll talk about later in this course. But they only exist for brief. Some of them only exist for brief periods of time. But in this course, first year chemistry, and most chemistry courses I've ever done, we typically deal with our naturally occurring elements, the sodium and carbon and nitrogen, oxygen, things we can find on Earth easily and naturally. All of these elements have distinct names and symbols, and this is for kind of like worldwide purpose. It's kind of like, why we have significant figure rules or why we use the SI system of units. So 1 meter in France is the same as 1 meter in the Middle East or Canada. Elements are the same thing. So when a chemist in Japan or Canada or America, USA, I should say, writes H or C, we know that they're talking about hydrogen or carbon. Some of these elements, and I'm going to give you guys on the D2L a little sheet of all of the elements that you need to know with their names. Some of their names aren't as easy as you would think. Right, like hydrogen. If you were going to shorten hydrogen, it's only common sense to just say H, right? H for hydrogen, very simple. Carbon, carbon, C, oxygen, O, nitrogen, N, very simple and common sense from the English names. Unfortunately, a lot of these are in English. There are words in chemistry that come from Arabic. The word alchemy is derived, from Arabic roots, and that has transformed into chemistry. So a lot of words that you guys hear, for Arabic speakers in this class that start with AL, so like alchemy, algebra, aldehyde, alcohol, algorithm, all of those have Arabic roots. The periodic table, not so much Arabic roots, but more English and a lot of Latin and Greek. So a lot of the old chemical symbols, chemicals that have been around for, well, I mean, all of these chemicals have been around for billions of years, but chemicals thousands of years ago, people knew, like gold and silver and mercury. They have a little bit more complicated symbols. Like gold, you might think if you were going from English, that gold would be G, right? Or GO. But nope, it's AU. And that comes from the Latin word aurum. AG is silver. So it's not S. S is sulfur. It's not Si. Si is silicon. So Ag is silver, and that's from a Latin word, argentum. Hg is mercury, from Greek hydrogerum, hard word to say. There's more, like Fe, ferrous or ferric, Pb for lead. Fe is iron, by the way. Pb, plumbum, I think that's Latin or Greek. And Pb is for lead. So these elements that you see written here, guys, this is a very important slide. These elements that you see here, I have a good question in the chat there. I'll get to this in a second. These elements you do have to know. I'm going to have to mute everybody. All right, sorry about that. I just put the class on mute for now. I have a question in the chat that says, do we have to memorize the periodic table for the test or quiz? And the answer is 50-50. You do not need to memorize the periodic table. The table will always be given to you. There's periodic tables in our classrooms on the wall. You guys will get paper copies of the periodic table anytime you do your test or final exam. If you're doing your quiz online, of course, you can use the D2L or Google. You will always have a periodic table, but you are expected to know what the letters stand for all of the ones that you see here. And it looks like a lot, but it's not as hard as it sounds. So on D2L later today, I'm going to post a PDF, a document that has all of the names of these elements below. So this is a document you guys can use for your quizzes online, but you are expected to know the names of all of these elements that are in black right here. So obviously not the blank spaces, but all of the other ones listed, you should know what the letters stand for. So rather than read them out to you in class, I don't think that's a valuable use of our time. I have a document that I've created that explains or lists all of the symbols with all of the names, and I will be sharing that with you guys today. So I'm going to move on from that because, again, it would really be no point for me to read all these out. You wouldn't remember them anyways. I have a document that lists all of these. You can use that document for your online quizzes for sure. You're going to need it for your next quiz, wink, wink. But on a test, you will be expected to know them. It's not as hard as it looks. It looks like there's a lot, but I mean, a lot of them are very common sense, like carbon, nitrogen, oxygen, helium, neon, chlorine. A lot of them come from their English names are pretty easy to remember. And they're chemicals you hopefully have heard of before. So on this slide, I pose a question. What do you notice about these symbols? That's a pretty open question. There's a lot to take from this, but I mean specifically, what do you notice about these letters? Almost like an English question. They all, first of all, yeah, so I'm getting, the question mass number and atomic number. Now, Warda in the chat has the answer I was looking for, and I'm very happy to see that. So in the chat, Warda said, they're all capital letters, and that's right. All of these elements start with capital letters, and the second letter, if there is a second letter, not all of them have second letters, but the second letter is lowercase. And you might be thinking, well, who cares? Why does that matter if one is uppercase and one is lowercase? This isn't English or communications class or grammar. Why does it matter? Well, I can show you why it matters really easily with this slide. The first letter is always capitalized, and by capitalized, it's a hard word to say, I think. I mean uppercase. If there's a second letter, it's lowercase. And just think of these 4 chemicals on the bottom. And there's a difference between the first 3 and the last one. Carbon, capital C. Oxygen, capital O. Cobalt is capital C, lowercase o. If you guys don't know some of these elements, you will by the end of this week, hopefully, because again, I'm going to give you the list of the ones you need to know, and you can use that for your first quiz, your second quiz. Your second quiz this week will be about naming some elements or writing symbols for elements. So you'll have a little bit of practice with this by this weekend. So, what about carbon monoxide? Now, carbon monoxide is different from the others. These 3 are elements. They are pure chemical elements. It is just carbon, just oxygen. But if we put carbon and oxygen together to make what's called a compound, or more specifically, this would be a molecule, but we'll get into that another day. But a compound, meaning 2 or more elements, we see that it's capital C, capital O. And I want you to really look at the difference between these two. It might not seem like there's a big difference, but if you write on a piece of paper CO, capital C, lowercase o, you're telling me or another science person, another teacher, another chemist, that it's cobalt. If you write capital C, capital O, because they're both uppercase letters, you're telling me that these are 2 elements together, which makes a compound, and it's carbon and oxygen. We call that carbon monoxide. We'll learn how to name how to name compounds a little later in this course. And in the chat, Aman asked the question, what about, carbon dioxide? That counts too. Carbon dioxide would be CO2. And we're going to learn how to name all of these things later in this course, not today. Naming will take us a couple of classes. So this leads me to the next slide, which is, well, okay, in nature, in your kitchen, in the food you eat, in the ground, in rocks, even in the atmosphere, a lot of these elements aren't just alone. Even in the atmosphere, it's not even just oxygen, it's O2. What we breathe in is not just O, it's technically a compound. We call it a molecular element, but I'll get into that later, but it is O2. So in nature, we find a lot of these elements grouped together with other elements. And when you have 2 or more elements held together by chemical bonds, we'll talk about chemical bonding later. I think maybe in chapter 4 or 5. We'll talk a little, maybe 3, but we'll talk about bonding in a month or so. But just know that if you have 2 elements that are attached to each other, 2 different elements, they make what's called a compound. And my most favorite example of this in the world is the one on the bottom. I really like the concept of food science, food chemistry. And as somebody who likes food a lot, this is a really cool example. Sodium metal Pure sodium metal, which we have in the lab, and I might show you in an experiment later this year, is extremely reactive. When you mix sodium metal with water, it tends to be explosive. It generates gas, it generates heat, and in large quantities, it can be explosive. So sodium metal, you can't eat it. If you put pure sodium metal in your mouth, it would burn your mouth. It's extremely volatile. I don't know if that's the right word, but it's extremely reactive with water. Chlorine gas. So here we have sodium. Here we have chlorine gas, Cl2 technically. Chlorine is a poisonous gas. I'm pretty sure it was used in maybe one of the World War I maybe, where chlorine gas is poisonous. If you breathe in chlorine, it's poisonous. It also reacts with water to make hydrochloric acid. So it's extremely toxic, poisonous, dangerous chemical. So think about this. Pure sodium metal, you can't eat it. Pure chlorine gas, it's typically a gas is how we find chlorine. You can't eat it. But you put those chemicals together and you get sodium chloride, my favorite chemical in the kitchen. You literally get salt, table salt. And guys, there's not much you eat in your life that doesn't have salt in it. From even cookies, bread, a lot of bread recipes have a pinch of salt in them. Food, meats, French fries, you guys know if you're like me and you like potatoes and French fries, they're covered in sodium chloride. Totally safe to eat, delicious, arguably essential for your body. You need some of these ions in your body to, keep healthy. So again, compounds are amazing. You take two deadly elements that will kill you and you put them together and you get delicious, delicious salt, table salt. I don't know. I always found that really cool. So guys, just a couple more slides. I'm going to finish this section and that'll be it for today because I do have a lab to get ready for. So just a couple more slides. And there's really one big thing to take from the next two slides. And it's this first law. The fact that sodium chloride is NaCl or water is H2O is really important. The ratio of these elements have to be the same. So, and I'll explain what I mean by ratio on the next slide. But if you change a chemical formula, so if I change a number or the ratio, or I change even the elements that are in it, I get a completely different chemical. It has a different name. It is completely different. And this is called the law of constant composition. And this is a law, wink, 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 you guys will need to know, maybe for a multiple choice or something on a quiz or test. The law of constant composition states that every molecule of a compound is made up of the same numbers of each element, okay? If you change the numbers of elements in the compound, you get a new chemical. So the composition of a substance, the makeup, the formula, the ingredients of a substance is always the same. And it doesn't matter if you find it on Earth, on Mars, from Canada to the Middle East, water is water, H2O. And I have maybe a better explanation here if you look at this slide. The formula for water, the law of constant composition says that water, one of the most fundamental, important compounds on Earth, has to be 2 atoms of hydrogen to 1 atom of oxygen. This is called a ratio, which you might learn about more in math this year, depending on the math course you're in. It's 2 to 1. The minute you change that composition, that ratio, you are completely changing the chemical. And this is another example I truly love because it shows how amazing chemistry is. I know I'm biased, but I love it because water, H2O, so two hydrogens, one oxygen, is a clear, colorless liquid that is essential for human life. I know it says there it's good for humans to drink. It's not good for humans to drink. It is essential, right? Without water, we cannot live. Plants cannot live without water. I mean, it's amazing. So if we change one little thing, we change the ratio of that formula and we add another oxygen. So notice hydrogen peroxide, H2O2. Two atoms of hydrogen to two atoms of oxygen. Or if any of you guys are math people, you could really just say this is 1-to-1, right? Every atom of hydrogen we have another atom of oxygen. Well, this chemical is completely harmful for humans to drink. If you drink hydrogen peroxide, you could die depending on the concentration and how much you drink, how strong it is, I mean. So really, really important. All molecules have a constant composition. Constant meaning it doesn't change. And if you change that composition, you get a new chemical. That's pretty much it for today. This last thing, this slide, we will come back to in Unit 3. But this basically is a little reminder, or maybe all I really need to explain to you today is when these elements get together, think about what an element is. An element is a chemical that cannot be broken down, or an element is a substance that cannot be broken down by chemical means. So when you write a formula for a compound, or when you're even just thinking about a compound, they have to be whole number ratios. Now, if you're not really remembering much from math, whole numbers, 1, 2, 3, 4, 5, 6, 7. No decimals. We can't have half of an oxygen atom, okay? Not by chemical means can we have, I could get really into what half an oxygen atom would even look like, but you can't have half of an atom in a compound. You either have it or you do not. So there is no decimals in chemical formulas. It's always 1, 2, 3, 4, 5, or 6. No, not 1.25, not 1.88. Nope. They have to be normal, easy, nice numbers. 1, 2, 3, 4, 5. And on, there's molecules that have 10 and 11, but usually just 1, 2, 3, 4, 5 in this course. We keep it pretty simple. That you don't need to know much else by this slide. We will look back at this in Unit 3. I'll talk more about what these masses mean. Okay, so I'll come back to that in Unit 3, but at the end of the year when you're studying, you can kind of look at this slide and it'll make a little more sense after we've done Chapter 3 or Unit 3, whatever. So guys, I'm going to leave it at that because I have a lab to get ready for, but I will answer a question in here from Warda. Does concentration have to do with the ratio of the mass? Concentration, and that's a really good question, we will look at in more detail at the end of the year, later. Concentration can mean a lot of things in general, but in chemistry, concentration is the amount of substance in another substance. And really the terms I'm looking for is the amount of solute in a solvent. So concentration, I'll get into later, but an easy way, and you just said insolvent, yeah, exactly. Just if anybody's not really connecting with that explanation, think of tea. If you guys drink tea or coffee, if you steep tea or make coffee and you have like 2 tea bags or a lot of coffee and you let it soak for a long time, the flavor molecules from the tea and the coffee get infused into the water. And if you have a lot of tea or a lot of coffee beans or tea bags, the flavor would be very strong. You might drink the coffee and be like, whoa, that is very dark or strong coffee. That would be concentrated, because concentration is the amount of something dissolved in something else. Okay, and it really, again, drinks are a good way to think about that. Back in Canada, I talk about Kool-Aid, but I've never seen Kool-Aid here. It's like a sugary drink. But I know people here drink a lot of tea. And the more tea that you put into the water, the stronger or more concentrated it will be. So when I said hydrogen peroxide concentrated, I mean like a lot of that chemical in water could kill you. And on that note, I'm going to have to go. You can ask any more questions. I'm going to stop the recording, and I hope you all have a fantastic day.